Hello, and welcome to our YouTube channel. In this video, you will learn how to operate the software for the motor test bench. You'll need two motion terminal windows, one for the drive side and another for the load side. The drive refers to the motor under test, while the load is the system provided by Solo. First of all, when we open the motion terminal, it's important to remember that if we mechanically adjust any of the motors, we must go through the calibration process. This process is explained in a separate video, so please refer to that before proceeding. Now, let's go step by step. Connect both the controllers one by one. This is the drive side. This is the load side. On the test bench side, we start with the configuration. We are using a 1 Newton-meter torque sensor, which means the peak torque value, as specified in the manufacturer's datasheet, is 1 Newton-meter. So we enter 1 in this field. The drive bus voltage is the voltage at which the drive side operates. Users must ensure that, whether using auxiliary inputs or the internal power supply, this value is entered correctly. In our case, the drive bus voltage is set to 48 volts. Now, we move on to underspeed and overspeed. You need to tune these two parameters in a way that constrains the drive side speed within safe limits. For example, if the reference speed is 1000 RPM, set the underspeed limit to 150 RPM. For the same 1000 RPM reference, set the overspeed limit to at least 1500 RPM. Now, let's move on to residual power consumption. Residual electrical power refers to the power consumed within the system that does not contribute to the motor's performance. That's why it's important to compute this value and subtract it from the final calculations. To compute residual power consumption, press this button. This is your residual power consumption of the system. Now, let's move to the Tune section. This section is used for configuring and processing torque sensor feedback. Kp and Ki are used to tune the controller. Kp determines how aggressively the system reacts to changes, while Ki affects how the system responds over time to achieve steady-state behavior. These values are typically tuned at our facility before delivering the system to customers. Acceleration and deceleration settings define how the drive responds to torque changes. Once the torque control parameters are tuned, acceleration determines how quickly the system reaches the target torque set. Deceleration defines how fast the system disengages when the underspeed limit is reached. Make sure to tune these values properly. In the pilot section, we have the main parameters for the load side. For example, we can enable or disable the load side if we want to run only the drive side and observe its behavior without any load. Torque reference is the target torque value for the test. For this model, 0.1 Newton-meter can be used, or a different value depending on the test setup and the motor's characteristics. The motor direction must be aligned. If the drive is set to rotate clockwise, the load side must also be set to clockwise. Once everything is set, we move to motor turning for the drive side. Now we go to the control section and check that we are in digital command mode. Ensure the control type is set to speed. Let's move to the test bench side. Start the generic test bench monitor. Here we have the computed values for residual power, and the drive's bus voltage is confirmed to be 48 volts. We'll proceed with this setup. Now go to the drive side and set the speed reference to 1000 RPM. Observe the change in the plot on load side. Next, set the torque reference to 0.1 Newton-meters to see how the motor responds. Press Enter and observe the plot. Now stop the monitor. Press Auto Fit Chart to adjust the view. You can also change the zoom level as needed. This is your test plot. In this plot, the yellow graph represents the speed of the system, which is at 1000 RPM, as observed. The orange graph shows the torque. This torque graph, influenced by the preset acceleration, is controlled up to a target torque of 0.1. The purple graph represents the electrical input power, which is the power consumed on the drive side. The green graph shows the mechanical output power, the power produced mechanically on the drive side. The pink graph illustrates the efficiency, which is calculated as output power divided by input power. Once the torque increases to a certain point, often referred to as the knee area, the motor speed begins to drop, indicating that the drive side is losing the battle against the load side. You can export the test data as a CSV file. When you export the data, only the visible portion of the chart, what's currently shown on the monitor, is included, not the entire chart. The error notification you see is due to the overspeed limit being exceeded. To proceed with future tests, make sure to press the Reset button. Now for the next test, which is at 2000 RPM. Increase the underspeed and overspeed limits accordingly. Set the underspeed limit to 300 RPM and the overspeed limit to 3000 RPM. All other parameters remain the same. Clear the monitor. Then go back to the drive side. Set the speed reference to 2000 RPM. Now, check the plot on the test bench side. Apply the same torque reference of 0.1 Newton-meters. Press Enter and observe the plot. Now stop the monitor. Press Auto Fit Chart to adjust the view. Adjust the zoom level to view the plot more clearly. This is your test plot. You can export the test data as a CSV file. Now let's test at 3000 RPM. For 3000 RPM, the plot appears like this. Similarly, we have tested the motor at 4000 RPM, 5000 RPM, and up to 11,000 RPM. So, these are the files containing the data for all the tests. For data processing, we don't need to be online with the controller. Simply go to the Data Analysis section and upload the CSV files. Now, the files are available here. You can choose any combination of parameters for plotting the axes. For the x-axis, choose velocity, and for the y-axis, choose torque. Make sure to select Use Absolute Values. You can now view the plots for each speed we've tested and see how beautifully they illustrate the motor's performance with various torque and speed ranges. This tool also gives us the option to pick custom colors for the plots. We can use various features like showing all data points or displaying average or mean values. There's also an option to smooth the curve to reduce sharp corners and make the plot easier to interpret. Now, we can change the axes. Set the x-axis to torque and the y-axis to efficiency. The plot now appears like this. Now, I've changed the x-axis to velocity, while the y-axis remains set to efficiency. So, the plot looks like this. We can also export the chart image and use it for data analysis, marketing, or presentations. This data was recorded with a resolution of at least 500 Hz or higher per graph. To learn more about operating this test bench, watch the other parts on our YouTube channel.